This video is for the physics lab looking at Kirchhoff's rules. In this lab, we are going to use a virtual circuit construction kit to build a complex multi-loop circuit that contains several resistors as well as several batteries, and use Kirchhoff's rules to analyze that circuit. Now, when you're constructing the circuit, you can choose from the circuit elements on the left side here. And to add a circuit element, like a resistor, you would click on it and drag it over with your mouse. And I would recommend putting the values on the circuit, so clicking the check mark next to values on the right-hand side menu, so that you can easily see the resistance of the resistors that you've added to your circuit. And if you would like to change the value of your resistances, which you will need to do because there are several different resistors in the circuit, then you want to click on the resistor, and then you can use the slider on the bottom. So in our experiment, R1, the resistor 1 in the circuit, is 120 ohms. So I'm going to set that resistance to 120 ohms. And R1 is roughly in this position in our circuit. Next, I want to add a piece of connecting wire. And if I bring this close to my resistor, then the connection sort of jumps together. If you would like to break a connection that was accidentally created, then you can click on the connection and a little pair of scissors will show up, and by clicking the scissors, that will cut the connection. Now, I do actually want those connected, so I'm going to just bring that back over here. Next, I want to add my R2 resistor. So bringing another resistor into the circuit and connecting it to the wire. And the value of R2 should be set to 50 ohms. So again, using the slider to adjust it to the desired resistance. And you can continue to do this as you build your circuit, continuing to add in the resistors and the wires as necessary. I also want to add in my batteries. So I'm going to add in the first one, which is V alpha. So the Greek letter A, alpha, is our first battery. And I want to be careful to add the battery with the correct polarity. So on a standard battery, you would normally see the little tab at the top and this gold barred end is considered the positive terminal, and then the black end is the negative terminal. And in our circuit diagram, the positive terminal is pointed up. So I want to connect the positive terminal here. And the value for V alpha is supposed to be 9 volts, so I don't actually need to change this one. And you will continue to add in your circuit elements and connecting them with your wires until you've built your completed circuit. So I went ahead and built the rest of my circuit, and you can see that I have all of my resistors in place and everything is connected with wires, and I have my various batteries placed in their correct orientation. Now, the first set of measurements I want to take is to measure the voltages across our 3 batteries. And in order to do that, I want to take my voltmeter out. So from our right-hand side menu, we want to access the digital voltmeter, and you can place it wherever you want on the simulation. And the procedure states that there is a red terminal To me, that looks a little more orange, but that is the positive terminal, and then there's the black terminal, which is the negative terminal. Now, when measuring voltages, keep in mind that voltage is always the same for two circuit elements in parallel. So your voltage measurements will be made parallel to the circuit element. And you want to connect the positive terminal to the positive side of the battery. So I'm just going to slide this over here. And I want to measure my first battery, so V alpha. I'm going to take the positive terminal, connect it to the positive end, and then take the negative terminal and connect it to the negative end. And then I can record the voltage reading as displayed on the voltmeter. Now this is giving me a reading of 9 volts, which makes sense because this is a 9-volt battery. And you'll want to repeat that measurement for all 3 batteries in your circuit. Once you've completed measuring the battery voltages, then you'll want to make measurements of the voltages across all of the resistors in the circuit. Now, the resistors do not have a designated positive and negative side until you place them in a circuit. And normally when we have a circuit like this, you can't actually see right off the bat which direction the current is flowing. But lucky for us, we are using a simulation, and we can take advantage of the show current option over here. And for a variety of reasons that I won't get into, we are going to be using the conventional current. And although that's not physically what's happening, the conventional current is the flow of positive charges. Again, that's not physical, but for a variety of reasons, we are going to be sticking with the conventional current. Now, when measuring the voltage across a resistor, the positive end is the end where the conventional current is flowing in. So if I want to measure the voltage across R1, then I want to take my voltmeter again, and I want to take my positive end and look at where the conventional current is flowing in. So that would be this end over here. And then the negative end is just where the conventional current is flowing out. That gives me a positive voltage reading for that resistor. And again, you want to repeat that measurement for all of the resistors in the circuit. So the positive end being where the current is flowing in, that being the conventional current, and then the negative end being where the conventional current is flowing out. And you can move the voltmeter around if the probes happen to be covering up the reading. So you will be recording all of the voltages for all of the resistors and all of the batteries. And that is actually the end of the measurements that you need to take using the simulation. Before you close the simulation, it would be a good idea to note the direction of the conventional current everywhere in the simulation and copy that into your circuit diagram, because the direction of conventional current flow is very important when figuring out your junction equations and your loop equations. Now, when analyzing our complex circuit, we want to use our Kirchhoff loop and junction rules. And I do not have a printer, so I made a hand-drawn version of the large circuit diagram. So the whole thing is here, but I can only show part of it at a time. So to begin, normally the first thing we'd want to do is choose a direction for the conventional current, because we would not know which way the current is flowing. So the correct method is actually just to guess and then see if you're right at the end. But lucky for us, we have our simulation that shows the direction of the conventional current. So I'm going to draw in little arrows to show my conventional current, and keeping the convention that resistor R1 has current I1 and voltage V1, resistor 2 has current I2 and voltage V2, and so on and so forth. So drawing in little arrows to show my conventional current and labeling the current according to which resistor it is flowing through. So when you are setting up your junction equations, you want to locate all of the points on your circuit where you have 3 or more wires meeting at a point. So point A is not a junction because there's only 2 wires, but point B is a junction because there are 3 wires meeting together. And we can use our junction rule and look at which current is flowing into the junction and which current is flowing out of the junction. So I have I2, which is continuing to flow over here. So I2 is entering junction B. Then I have I3, which is flowing out, and I9, which is also flowing out. So I can write my first junction equation down below for junction B. And I have that the total current in is equal to the total current out. So that looks like I2 is equal to I3 plus I9. So that would be my first junction equation. And you would go around your circuit and identify all of the other points where there are 3 or more wires meeting, and using the conventional current and whether the current is flowing in or out of the junction, then you would use that to write the rest of your junction equations. Now, before we can write our Kirchhoff loop equations, we need to establish a sign convention. And there are different ways you can establish a sign convention, but one that I would suggest you use is the following. So if we traverse an EMF, meaning a battery or a power supply, from its negative to its positive terminal, then you would have a positive voltage. If we traverse an EMF from positive to negative, then that would be a negative voltage. And if we traverse a resistor in the same direction as the conventional current that is flowing through it, then the voltage is negative IR. That comes from Ohm's law, where V equals IR. And then if we traverse a resistor in the opposite direction as the conventional current flowing through it, then that voltage is positive IR, again, coming from Ohm's law, that says V is equal to IR. So now that we have established the sign convention for our Kirchhoff loop rules, then we want to go around our loops and write our loop equations for the sum of the voltage drops and gains around that loop. So I will go over the very first loop that you're asked to verify. So the first loop that we are going to verify is loop ABHGA. That means you're starting from point A, going to point B, down to H, over to G, and then finishing up back over here at A. So starting at A, if we travel in this direction from A to B, then we are traversing resistor number 2, and we are going in the same direction as the conventional current. So that would be a negative voltage. Then we go from B down to H, and we are traveling through two resistors, R9 and R10. Both of those are in the same direction as the current. So again, it will be a negative voltage for R9 and R10. When we get over to H and we want to travel over to G, again, we are traversing a resistor in the same direction as the current. And so that will be another voltage drop. Then the last part of our loop is to go through our voltage supply, or this is the battery, VA. And in our simulation, we have the negative end of the battery here, and the positive end is up here. So because we are going through the battery from its negative to its positive terminal, then that is a positive voltage. So it'd be positive V alpha. And then finally we are going through R1 in the same direction as the current. So that will give us a negative voltage from R1. So if we write this in an equation, then it would look like this. So we have loop A, B, H, G, A, and we have the sum of the voltages around the loop. So the first thing we encountered was R2, so that is going to be negative V2. Then we encountered R9, and that was also a negative, so negative V9. Next was R10. That was also negative. We have negative V10. After that, we went through R7. Again, another negative. That was negative V7. Then we passed through our battery, so V alpha, and that was a positive voltage. So we have positive V alpha. And then we passed through resistor 1. So that was once again a negative, and we have negative V1. And what we are trying to verify is that the sum of all of the voltages, positive and negative, as we traverse that loop, that sum should be equal to 0. So using the measured voltages from your simulation, as well as their uncertainties, you want to verify that this equation does in fact agree with 0 within uncertainty. And then you'll repeat that process for the rest of the loops that are listed in the procedure. So again, going around your circuit diagram, making sure that you're paying attention to the direction of the currents and whether you are passing through a resistor, if you're going in the same direction as the current or in the opposite direction as the current. And then for the batteries, whether you're going from negative to positive, or if you're going the other way from positive to negative. So you will write out all of your equations in their variable form. So the way I did for our first loop here, you're going to write out those equations in their variable forms first, and then verify whether or not the voltage sums agree with 0 within their uncertainties, and that will verify the loop rules for this experiment.